Alright, welcome back to our final installment in our curve sketching series. And we've arrived at graph sketching in its entirety. So we're going to take everything we've been discussing, the first derivative test, the second derivative test, asymptotic behavior, maximum minimum values, x-intercepts, y-intercepts, and behavior, and concavity to sketch the most complete curve you've done thus far in your career. But before we get there, let's just touch upon some last minute details. Okay, a little chart here to a little graphic organizer to help us when we are sketching our curves. So if we have a first derivative that is increasing and a second derivative that is positive or concave up, our graph will have this type of shape. If our first derivative is still positive and increasing, but our second derivative is concave down, our graph will look something like this. If we have a first derivative that is decreasing, but a second derivative that is concave up, we will look something like this. Positive, 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 negative, and negative, negative. And vice versa, we have both a first derivative that is decreasing and a second derivative that is negative. Concave down will look something like this. Okay, so keep this in mind as we begin sketching our functions. And just a reminder that asymptotic behavior is the behavior of the function as x approaches positive, negative infinity, or a vertical asymptote. This is something we definitely want to keep in mind when dealing with rational functions. And one final piece of information, just in case you have forgotten, assuming we have some ambiguous polynomial function that we're going to define as f of x equals a n x n plus a sub n minus 1 x sub n minus 1 some constant. Okay, so there's some degree n, and then obviously one less than the degree and two less than the degree and so on and so forth. We have four types of n behavior. This looks like a graph, so let's make it look more like a box. Okay. In the event that we have a positive leading coefficient, but we have, let's say, an odd degree, our function will look something like this. Let's say that we have, once again, a positive leading coefficient, but n is even. It will look parabolic. If we flip the script and we have a negative leading coefficient, but n is once again odd, we are just going to reflect over the x-axis, so our graph will look something like this. Obviously in the middle will look different. We're just talking about the n behavior here, and vice versa. Our even degreed function will point downwards. So that information is our final tweaks to tighten everything up, and now we are finally going to begin graphing. A lot of information that we now must acquire. Let's say we had something along these lines. X squared minus 4x plus 3. Yes, I know, very trivial, but this is where we're going to start before we delve into more complex functions. First and foremost, we can see that our y-intercept is 0, 3. And our x-intercepts, if we factor this, are at x equals 1 and 3. Let's take the first derivative, see if there's a max or minimum value. 2x minus 4, so x equals 2, right, because we would set this equal to 0. This is a critical point. So at this point in time, you could apply the first derivative test or wait to do the second derivative test. I personally like to do the first derivative test. So n prime of 0, n prime of 3. If I substitute in, this is 0 will yield a negative value, and 3 will yield a positive. Negative to positive means I'm going to have a min at x equals 2. And then I just need to check my concavity, so f double prime of x equals 2. And since this is a constant value, that means this will be concave up. And if we go to, oh man, I have no more room. Let's see, let's delete this piece here. Yeah. And if I were to graph this, right, I got an even positive leading coefficient. Y-intercept at 0, 3. And x-intercepts at 1 and 3, 4, 5. I knew that I had a minimum value at x equals 2, so if I plug that into the function, 2 squared is 4, minus 8, negative 4, plus 3 is negative 1, so 2, negative 1, right? And my graph will look something along these lines, once again indicating, right, that this function is going to be concave up across the entire domain of real numbers, and then that we had obviously a negative function behavior from negative infinity to 2, as we can see here, and then positive function behavior from 2 onwards to infinity. But once again, a much more straightforward function. If we were to alter the degree, let's say that we had a function that looked like this, 3x to the 4th minus 8x cubed plus 6x squared plus 1. We can clearly see we'll have a y-intercept at 0, 1. In this case, I'm not really going to worry about the x-intercepts because I'm not concerned with that. But I am concerned with increasing and decreasing behavior of function. I know there's a positive leading coefficient with an even degree, therefore I'm going to have parabolic behavior. If we take the first derivative, 12x cubed minus 24x squared plus 12x, and set that equal to 0. I can factor out a 12 and an x squared minus 2x plus 1 equals 0. So my critical points will be at 0 and then 1. You can factor this as x minus 1 squared. So if I were to check that, 0, 1, once again, only focused on the sign of the output, not the actual value. So negative 1 will make this negative. I'll have a positive 1 plus 1, that's 2. Negative times negative 2 will become positive, so positive times negative, negative output. If we do the positive 2, this is positive, this will cancel, and we're left with a positive. If we do 0.5, this becomes a 1. Right, so negative 1 plus 1 cancels, positive, positive, positive. So nothing here, no max or min. But we have negative to positive, so that means we have a minimum at this value. So that means 0, 1 will be our lowest value. We must now check concavity. So I'm going to derive this, 36x squared minus 48x plus 12, and run that same process, 3x squared minus 4x plus 1, and set that equal to 0. Right, in doing so, I can factor this as 3x minus 1, x minus 1. And you can clearly see that at x equals 1 and 1/3, we have potential points of inflection. So once again, we're replicating the process here for the first derivative. We could do the two birds with one stone second derivative test, but I'm not fond of doing that. I like to separate my processes. So I'm going to check f of 0, f of 2/3, which is annoying, and f of 2. Once again, looking for a change in behavior of the second derivative. I can just substitute in here. 0 will give me a positive 1. 2/3 will give me a negative. And 2 will give me 4 times 3 is 12 minus 8, so that's going to be a positive. So the good thing, I guess it's good, is we'll have actually points of inflection at both of these values. We can see that we'll be concave up from negative infinity to 1/3, and from 1 to positive infinity, but concave down between 1/3 and 1. This is all information that needs to be included in your solution paths now that you've arrived at calculus. Okay? I'm obviously not going to write it out because I don't necessarily have the board space. But you could also calculate what the outputs are at those values. It just kind of helps to, demonstrate the concavity. So at 1/3 we have 38 over 27, which is really 1 and some fraction, and f of 1 is 2. If I were to sketch a loose graph of this, right, because once again, we're not Desmos. Your goal isn't to give me the this pristine picture of this. It's to include all the information that would get me that pristine graph. So once again, minimum, right, at 0, 1. I know it's parabolic, so I'm coming down this way. I'm coming up. I know that at f of 1/3, I'm a little bit bigger than 1, so if I put 1 here, let's say that this is 2. So I'm here. And then at f of 1, I'm really at 2. Right, so, okay, something along these lines. That's a 1, negative 1, so on and so forth. If you want to include that in. Okay, but once again, it's more so about this information that we are now seeking. The picture obviously has to match, but it doesn't have to be pristine or perfect. This by no means, or stretch of the imagination, is remotely equivalent to what you would get if you substitute that into Desmos. We're going to pause there, and then we'll pick up with part 2 with more complex functions.